Uh, Good morning, guys. Today our topic is Maxwell inductance bridge. You have seen in previous classes, it was Maxwell inductance capacitance bridge, but today we are going to study the Maxwell inductance bridge. You can see in this picture, this is the Maxwell inductance bridge, and now we can determine a unknown inductance by only varying the known resistance and the known inductance only. No capacitance are there. Okay, so you can see this is the our diagram, and uh, we just going to calculate it. Look, and this is, we know this is L is unknown, L1 is unknown inductance, and it is to be, it will be measured, and R1 is the resistance of the unknown inductance. We know every inductance has some resistance. This is the R1, but we are separately find it out. We can find it out. And now the R3 and R4 are the standard non-inductive resistance. R2 also the standard variable resistance. Okay. And now L2 is the standard variable L inductance. This is the L2. Oh, L2 is the standard variable inductance. Okay. With the fixed resistance R2. It has some resistance. This is the fixed resistance, that is R2. And then from the figure, you get the impedance of the respective arms are given as, how could I give? Look, this is the Z1, this is the Z3, this is the Z2, and this is the Z4. This is the impedance. Okay. Now we can write that Z1 equal to R1, okay, plus J omega L1, J omega L1, because this is L1, L1 is there. So total impedance is Z1 is defined as like this. And now Z2 is here, just like same. Z2 equal to R2 R2 plus J omega L2, but here another R2 is there, so we have to put this small R2 over here, because this small R2 is there, and this is the capital R2, this is the another resistance, this is the variable resistance. So we have put like this, and we know basically this is the Z3. Z3 is only the R3, because there is no inductive or capacitive reactance are there. So, and so this is Z4. Z4 is also like this. This is only R4, because only resistance is there. These are the fixed resistance. Now under the balance condition, when it will be the balance condition, means D deflector D will show the null deflection. In this condition, we know the balance condition. This is called balance condition. We, okay, under balance condition, what happens? What is the conditions to be balanced? That is, the cross arm multiplication is equal. Okay, so Z1 into Z4 equal to Z2 and J3. So cross arm multiplication, J2 J3. Look, this is the cross arm multiplication, and this is the Z1 into Z4. So cross arm multiplication should be equal. This is cross arm multiplication should be equal. So this is the conditions. Now, as per this condition, we can write the value of this Z1, Z2, Z3, Z4. Then we can get the total equation. Look, So we can write, we just put the value of the Z1 and Z4. Look, this is the R1. I am putting the value of the Z1 into the Z4, L1 into Z4. Z4 means that is only R4 equal to Z2. Look, Z2 is here. Z2 equal to R2 plus small r2 j omega L2 into Z3. Z3 means only R3. Okay. So if we multiply this, means total we have to multiply this. Okay, guys. Now, so we are getting from here R1 R1 R4 minus j omega L1 R4 equal to R2 R3 plus R3 small r2 j omega L2. Okay, so we can, if we rearrange this, why we need to rearrange this? Always remember that we are going to separate the real part and the imaginary part. Okay, that's why we need to do this. Look here, it is the plus, not minus. So what happens? These R2, R3 coming here. Okay, or we all we all bring this right side part to the left side part. So what happens? So R1, R4 minus R2, R3, that is, and we get minus, because this part is coming here and we are getting common part. Okay, this is all are zero because all parts are coming here, and then we are taking some common factor and then we get this. And from these cases we getting this part are real part. Okay, so we can write, we can separating the real part and imaginary part, we are getting R1 R1 R4 minus R2 R3 minus R2, and this small and capital, this is 0, this is real part, and from this real part we are getting R1 R4, we are taking this part, again right hand side so that we get the positive sign. So R2 R3 plus small r2 capital R3. Okay, from this equation you can see, from this equation, and this R3 R3 are common, and we now we can find out the unknown resistance R1. R1 is just taking the common, this is the R3, and if we get the common factor from these two part, we get only R2 plus small r2. Okay, and this R4 is coming, here, so it is divided by R4. So we can find the unknown resistance, that is R1. R1 is R3 by R4 multiplied by R2 capital R2 plus small r2. Okay, this is our unknown resistance, but we need to calculate the our known unknown inductance also. Okay, and we can see if we separate the imaginary part and the imaginary part, and if we separate the imaginary part and the real part, then we separate the real factor means resistance and imaginary part, and this is the inductance. So this is the imaginary part. So from here we can find, that is, look, this part is also 0. So j omega into L1 and R4 minus L2 R3 is 0. So j omega also becomes 0, because from here you can find it out. J omega into, this is the imaginary part, R4 minus L2 R3 equal to 0. So if this part is coming here, then it becomes 0. So we are getting L1 into R4, sorry, this is minus L2 R3 equal to 0. So L1 into R4 equal to L2 into R3. So L1 equal to L2 into R3 divided by R4. So we can find the L1, we can find the unknown inductance L1, which is L2. This is the known inductance, and this is the variable inductance also, and the fixed resistance R3 by R4. Okay, so this is the easily solve out. It is easily solve it out, and we can find the unknown inductance. So this is the Maxwell inductance bridge, and this is very popular bridge, and for calibration purpose we are finding it out in various R&D sections. And guys, if you have any question, you may ask me, and then I am going for the Phasor diagram, how to draw the Phasor diagram. Look, here another arms are not there. If you go for an Desauty bridge, is Anderson bridge, there you can find another arms is there. But this is a simple four arms, and we can find the Phasor diagram. And step by step, we have to learn how to draw the Phasor diagram. In previous few previous class, I have discussed how to draw the Phasor diagram, because basic rules of Phasor diagram. Now here, hello, बोलिए. Just 1 or 2 minutes. I am showing you the Phasor diagram. Okay, guys, if you have any question regarding this, then you may ask me. Okay, now we are going to draw the Phasor diagram. How to draw the Phasor diagram? Okay, so you can see, look, in this diagram we can find first step by step. Guys, just try to watch this very carefully, so that once you can draw this Phasor diagram in your own, you can draw every Phasor diagram for every bridge, because somewhere it is very much difficult. Okay, so look, step one, we are taking this, this is first, this is the E1, this is the E3, because the potential difference from this point to this point is E1, and potential difference from point B to C, this is E3, and potential difference from A to this D, this is the E2, and from D to C, this is the E4. This is the potential difference, or you can say this is the E. Okay, and so what is the balance condition? Balance condition is, for balance condition E1, sorry, for E1, for E1 equal to E2, E1 equal to E2, and simultaneously E3, E3 equal to E4. This is the balance condition for the potential difference. Now, for we are taking and this case is AB, AB. This is the U1, U1 as a reference condition, reference state. So, what happens? Just draw this I. This is okay, and I1 R1. Look here, it is flowing the I1 current. I1 current, you can see this I1. So I1 R1 and is just phase. This is the I1 current. We are taking this reference. I1 here current is reference. Okay. And so we are taking I1 is reference. So this is I1 R1. It should be just in phase. This is I1 and this is R1. This is just in phase, but here it is the omega L. Look, the potential, this is V and I are, this is also potential drop, but this is I1 R1, this is purely resistive, so it is in phase. But in case of L is not, means potential drop in the L is not at phase, it should be 90-degree. We can see, if taking the reference of V, then I, for the I, for L, for inductance, that is 90-degree lagging, 90-degree lagging. So what happens if I is reference, then V is 90-degree leading. So if I get this I is reference, I is reference, then V should be 90-degree leading. So here is same things is happens. You can see, you can see here, this is I1 R1 and this is, sorry, this is due to omega L. This is due to omega L. This is, this is I1 omega L1, I1 omega L1. Okay, because this is potential drop across this is inductance. So it is 90-degree leading by this current. Now, so what happens for this case? What is the E1? E1 is just like this. E1 from, look from this Phasor diagram we find everything. This is the E1. This is the E1 because U1 U1 is the I1 R1 plus I1 omega L1. So these two current and this two potential drop implies this E1 because here only two elements is there. So this is showing because the vector sum is there, E1 is the just like this. This is the you can this is the step one. Okay, now we are finding the branch current for the E1 one by one. Just we are getting for the E1, then we are going for the E2 or the sorry E3, then we are one by one we are just closing the circuit. And now for the E2, look, E1 equal to E2, E1 equal to E2. Balance for the balance condition, E1 equal to E2. So here we can write, and this is the reference line. This is the reference line. We are getting black. This is the reference line, and we have given that is E1, that is E1, that is I1 R1, that is I1 omega L1. Look, step 1, step 2, you can find that is step 1, that is step 2. Okay, so U1, U1 is here. We know U1 equal to E2 for the balance condition. U1 equal to E2. So we can write that is U1 equal to E2. Okay, U1 equal to E2. U1 equal to E2. Okay, because this is given. So I1 omega L1 equal to I2 omega L2, I2 omega L2, and I1 R1 equal to I2 R2, I2 R2. This because this is E1 equal to E2, so everything should be equal, means the summation should be equal. So we can find out that is E2 is just I2 R2 plus I2 omega L2 because U1 equal to E2. And now I1 and I2 are the same phase, and both the branch are same. Why this is I1 or I2? Because this is branching current. This is I1, this is I2. So this is in phase, and the magnitude of the I1 and I2 depends on the value, and it may vary. So if I1 greater than I2 or sometimes I1 less than I2. Okay, that's why if it is I1, if you put that is I1, then you have to put I2, or sometime you can change as per the value. But what happens? I1 R1 equal to I2 R2. If I1 is greater than I2, then R1 should be less than R2 because we have to make it equal. If I1 is greater, then it should be, and it is less, then it should be also such a way that it should be equate. If it is greater, then it should be less, and if it is greater, then it should be less. In this way, we just equating or equilibrium. Otherwise, then E1 equal to E2, this condition will not fulfill. Okay. Now for the step 3. In this case, what happens for the step 3? We are going to step 3. Look, in this case, you can just see this step 3. Only this current is flowing. Only the I1 current is flowing, because here I1 current is flowing and this R3. So what happens? Just taking this R3, I3, sorry, I3 and E3, that is E3, because this is in phase. E3 means I3 into R3. IR drop means, so this is the Phasor diagram for the this branch. And look, we know that is I3 equal to I1. Why? In this branch, this is a series current. This I3, this is flowing I3, and this is the I1. So I1 equal to I3, or you can say this is directly I1, because this is only series, because if there is a no deflection, there is no path is there. So this circuit became a series. This is forming a series connection. Okay, so I3 is just I1, or here you can see there is no I3, only I1 it is written, because this is a series circuit. So we can write I3 R3, and the I3 are in phase, and it is a resistive circuit. That's why the phasor diagram is just like this. So how could I write this? Here I1 is there, so I1 is there, then R I3 is there, because I1 equal to I3, same current is there. Okay, so this is the I1 R, this is the I1 and R1, and just 2 minutes. This is the I1 and R1, and just like this is also the E3, because E3 is also there. E3 is also there. That is E3. That is I3, A3, R3, or you can say that is I1, R3. Okay, or you can say or I1, R3. So this is the Phasor diagram of this, and this is I1, R3. And if I go for the clear this, you can see the clear. Look, sorry. Here first we are getting, that is I1 R1 equal to I2 R2. Here this is I1 current, I1 current. Now I1 current means I1 I3, and this is the I2 current. Okay, I will come I2 current, and this is I1 R1, this is I current is flowing. So this is the another is there, that is the I1 R3, or you can say that is the I3 R3, or okay, I am doing this in the different color. Okay, and just like previous, it was the I1 I1 omega 1 omega L1, and that is I2 omega L2, and this is our E1, this is our E1, U1 equal to E2 also. Okay, this is the Phasor diagram, but E3 is there. Look, this is the E3. Okay, E3 is there. So E3 up to this, and this is the I1, I2. Okay, and this is I1, I3. And just like this, E4 and the arm 4 for the 4. This is also resistive. So we can find that is I2 is the same current is flowing. So I2 current is also flowing here. So this is the I2 and this is also I2. Means here should be the I4. Means arm 4 current is flowing I4, but I4 is the just like I2 because there is a no branching is there because this branch is not there at the balance condition. So only this I2 is flowing in series. So I4 and I2 is equal. So we can also write that is if there is a I4, if there is a I4, then the potential drop E4 is also fetched because I2 I R4, or you can write that is I4 and R4. Okay, so we have to write this. If I put this is the I2, because after I1 this is I2, sometimes I1 is greater than I2, sometimes I2 less than I1, whatever we are taking this like. So it is also doing this. Okay, and now we can put that is I1 I2 equal to I4, I1 equal to I4. So here is also another part is there, that is this E4. Okay, and we know E3 is the E4. So here is the E3 and we can put the E4. So ultimate what happens? Ultimate it you can see this is E3 equal to E4 from this E3 equal to E4, and this is I1 R1, this is I1 equal to I3, and this is I2 equal to I4. So one by one, if I do this, this is the omega L1, and this is E, this is E. Okay, this all are meet over here, and I want to draw this properly if time permit. This is E1, and now this is the E. Okay, and this is the E1 equal to E2. This is E, and this is E3 equal to E4. So here is the Phasor diagram. That is the Phasor diagram. Okay. So guys, I think you can understand these things, and just I want to draw this properly because it is not. Okay, so we got this. That is E3 equal to E4. Okay, and from here another line is getting, that is I1 R1 equal to I2 R2, and from here we got another line, that is I3 I1 equal to I3. From here we another line we got, that is I2 equal to I4. Okay, so here that is I1 omega L1, that is I2 omega L2. Okay, so here we can find, that is dotted line here, that is E1, that is E1 equal to E2. Okay, E1 equal to E2. So here we can find, so here is the E1, here is the E1, sorry, here is the E. This is our main motto. Okay, so guys, this is our phasor diagram of this Maxwell inductance bridge. This is E3 equal to E4. This is also E3 equal to E4. Okay, so guys, if you have any question, you may